All right, so thanks a lot for inviting me, Merced. It's good to meet you. I always give a talk and I never get to the acknowledgements, so I wanted to put the acknowledgement slide first. This work would not have been possible without the encouragement and help of my friend, Dan Zalit, who works at SVB Analytics, and some startup funding from UC Merced. If at any point you'd like to read more about this, the work that I'll be talking about today, you can download the paper off my website. It's a paper that was accepted at a data mining conference, predicting private company exits using qualitative data. All right, so let me just jump right in. This talk's going to be about predicting what startup companies do based on the companies that have funded those startup companies, so the venture capitalists. VCs or venture capitalists put funding into startup companies, and they don't just sit back and watch. They'll sort of demand a seat at the table, and they'll ask to be consulted on important business decisions. And so what this slide is really all about is that based on the VC that's funding the startup, you may be able to tell how the startup is going to do, simply because VCs bring a lot of experience and in-house expertise with them. And so essentially, having a really knowledgeable VC on your board of directors as a startup company may greatly influence your future trajectory. Okay, so kind of based on this idea, the question to ask is how much do they influence the future trajectory? And to phrase this as a data mining question, if you know who has funded a startup company and you know when the rounds of funding have occurred, the question is, can you predict how that startup company will do? And more specifically, can you predict whether the startup company will go bankrupt or not? Right? That's really kind of the zeroth order question you would like to know. And more specifically than that, I mean, you don't really want to have an answer to the question that depends on knowing, say, the first 10 rounds of funding that have gone into a startup. You'd like to know what the startup's going to do, given as little information as possible. Right? So if you just know the initial 2 or 3 rounds of funding and you can make this prediction, this might actually be kind of useful. Okay, so useful to who? You might say, well, the goal here is really to seek insights that could help venture capitalists make better investment decisions, or you could view it as giving advice to startup companies to tell them which VCs they should ask for funding. Okay, and so there's a couple of other goals here. There's been a lot of work in the social science literature, it turns out, on networks in the venture capital community, looking at different factors that might influence which VCs make investments in which firms and whatnot, so we can kind of touch on some of those issues. And there's also the fun math side of it. Since I am an applied mathematician, I have to say that it's a lot of fun to work on this. Okay, so what did we do? We grabbed a lot of data from this academic website. A lot of academic libraries have access to this. Thomson One Venture Expert. UC Irvine does. Berkeley's Haas School of Business does. Stanford has access to this database. The data comes to you in Excel spreadsheets, which is a little bit annoying. I'll get to that later. And so what is on a spreadsheet? Well, typically you get the inception date of a startup company. Okay, there's one spreadsheet per startup company. You get the inception date, you get how many rounds of funding went into the startup, and you get the dates of when they received their funding. You get a code which describes the company's sector. So, for example, it could be biotech, pharmaceutical, IT, energy. You get a list of investors, which is really the most interesting information here, and you also get the exit code. Okay, the exit code it really is a qualitative label of how the company ends up doing. Okay, so some possible exits that you might talk about are bankruptcy, IPO, where the company goes public, starts selling stock, a merger. You could have a leveraged buyout. That's where someone comes in, buys all the assets, and sells them at a fire sale. And then you have this whole concept that maybe the company doesn't exit the private space at all, but stays private. So kind of nothing happens. Okay, so we download all this data. We have data on 77,000 different companies. There's 12 exit codes in the raw data. We bucket that into 5 categories. And actually, we're going to further reduce this down into two binary classification problems. The first one is telling whether the company will go bankrupt or not. And the second one is to determine whether or not the company will make some kind of an exit, whatever it is, or whether it will remain privately funded. All right. So this is really a classification problem. And the idea of how you might use this is a potential mid to late stage investor who knows what the startup company has done in its first 2 or 3 rounds of funding and knows who the investors were in those early rounds and knows when the rounds occurred and so on. They could use this model as a way to assess, say, the probability that the company will go bankrupt or the probability that the company will make an exit. So this could be used, for example, to assess the loanworthiness of a startup company, or for a startup company, you might run this scenario and say, well, if we get money from these VCs, maybe that'll decrease our probability of going bankrupt. Okay, so in terms of how many rounds of funding you want to use, one thing we looked at the data and kind of told us that 84% of the companies have only 3 rounds of funding reported. So that seemed like a pretty reasonable number. There is one company in our database that has 27 rounds of funding, which is a little ridiculous. The data is survey-based, though. So that's kind of an important thing that needs to be mentioned at some point. You don't really have perfect vision, right? This is a real-world, kind of incredibly messy data set. People might inflate all kinds of things on this thing. We're not using any quantitative information here. So we're not using information about, say, revenue in millions of dollars or anything like that, which could be completely inflated since it is self-reported. But one thing you're going to find out is that the database is very lean, relatively speaking, on bankrupt companies. Because if you've gone bankrupt, you're not going to volunteer your information to Thomson Reuters. Maybe not, anyways. That's my theory. Okay, so let me also just go on and tell you more about the data set. There's 9,564 unique investors. Okay, so there's a lot of VC firms out there. There's a lot of private equity funds that are represented here. There are 9 possible sectors. I already said there's 27 rounds of funding. One company had a round of funding in which 31 investors participated, which is also ridiculous. Usually this number is around 4 or 5. So there is another database that I don't have access to that explains how much was invested by each investor in each round of funding. That would be really useful information, but I don't have that. So you look at the data and you ask yourself the question, how do we represent this? Right? How do we turn this into something where we can actually mine the data and get some important insights? And let me just go through as kind of a case study and tell you something that did not work. Okay, so this is actually a very commonly used method in text mining, and it works really well for a lot of problems. It's called a bag of words representation. Okay, so this is where you take your company and you look at the investor list and you say, well, there's 9,565 investors. I'm going to represent that by a binary vector. And I'm going to put a 1 in the appropriate slot if investor J invested in the company. Okay, so every company's investor list gets encoded as this binary vector. This gives you a huge sparse matrix. And you can turn this into a classifier in any number of ways. An idea that immediately comes to mind and is kind of written about in a lot of books on data mining is to basically split your giant matrix into 2 matrices, one of which consists only of the bankrupt companies. The other one consists of the non-bankrupt companies. Take the SVD of both of these matrices. Right? That'll give you 2 different bases. You can think of it as kind of the bankrupt basis and the non-bankrupt basis. And then sort of given a new company, you try to represent the new company in either of these bases and see which one approximates the new company the best, and that's your class label. This is a pretty commonly used technique. It turns out this works horribly here. So we tried this, and we formed some hypotheses. We learned from this kind of colossal failure of the bag of words representation that it ignores a temporal structure. Okay, so one important thing here is that some investors invest early, some investors come in later, and that structure in time could actually be really important, and that's ignored in the first encoding of the data. The other thing that we realized is that the investors were not ordered meaningfully. So we didn't rank the investors in any important way. We just kind of ordered them alphabetically. So we need kind of a better way of representing the data, so that motivates the next thing I'm going to talk about, which is a social network ranking. Okay, so this is where you take all of the investors, all 9,564 of them, and represent each investor by a vertex in a graph. So these are three possible VCs. Kleiner-Perkins may be familiar to some people here. And this is actually the investor network for Groupon. Okay, so these three companies all invested in Groupon, so we connect the vertices by edges. So basically, if you've co-invested in a round of a company at some point in time, I connect your vertices by an edge. Okay, and then that gives me an automatic ranking of investors based on the degree. And that's definitely more meaningful than an alphabetical order. How meaningful it is, we'll tell you later. But let me just tell you one thing, which is that when I do the social network ranking of venture capitalists, one really interesting thing that happens is that you get a top 10 list, which actually corresponds rather well with kind of just an eyeball metric, just an intuitive feeling of what exactly the important VCs are, of who exactly the important VCs are. Okay, so you have Kleiner-Perkins here, Sequoia Capital here, Goldman Sachs. I have some big names, and they show up kind of at the top of the social network ranking. The top two over there are kind of artifacts of the data, right? So the fact that the number one entry is undisclosed, that just means it's survey-based, and a lot of people didn't want to say who's investing. And individuals, that's because if you look at the bar graph I showed earlier, most companies only last one round. And so the first round is going to include those angel investors. So there's a lot of companies that get one round and go nowhere. Okay, so how do I represent one round of funding in this kind of new methodology? Well, what I do is I say each round might have 31 investors. So I'm going to map each investor's name in the investor list to an integer given by the social network ranking. There's also a type that I get from the database, which is either early stage, mid stage, late stage. There's a bunch of different types. And so each round gives me a vector of length 62. And one thing to note about this encoding is that if you have a small number of investors that participated in the round of funding, so if you only have 5 investors, you're going to get 5 ranking integers and 5 types. That's going to leave 52 entries missing. Okay, so in a nutshell, I think this is why this encoding is not used more often, is because we automatically incur a tremendous amount of missing entries, right, in the matrix. So, I mean, a bag of words does not have this problem. Okay, so how do we represent all of the data? Well, I just told you how I represent one round. So one round corresponds to 62 attributes. I do that for 3 rounds, and then I append to that, actually prepend to that, a little bit of static information, which is the 4-digit sector code, the inception date, and the rounds at which the company was funded. And so I get 193 attributes. The first one out of those attributes is the exit code. So I'm not allowed to use that when I build a classifier. Right? That's the thing I'm trying to predict. I guess I had to have one sort of flowchart in this to sort of keep up with everyone else's talk. But yeah, so I've got these Excel spreadsheets. I go to a database in Python. My Python database gives me files that I can then mine using either R or Weka. I've got a lot of R code that I'll tell you what it does in a second. Different sectors behave differently. This slide is meant to tell you that, in the pharmaceutical sector, leveraged buyouts are not very common, but in, say, industrial and service companies, leveraged buyout is much more common. So it makes sense to model the different sectors differently. So I'm actually going to build 9 different models, one for each sector. So let me tell you about another issue that we faced, which is that when we do cross-validation, okay, which is how we assess the out-of-sample performance of the model, it turns out that if I train the data, if I train the model, whatever model I use, if I train it on the raw training set, there's this tremendous issue that I face because only 12% of the companies are bankrupt. Remember, I'm trying to solve the bankrupt versus non-bankrupt problem. Okay, so that means you're going to get more often than not, a classifier that wants to predict non-bankrupt every single time. Because automatically it'll be right 88% of the time on the data set. Okay, so this imbalance in the class distribution gives me a huge generalization error because the algorithm isn't learning anything. It's just spitting out non-bankrupt every time. It's not even looking at the features. So the way I get around that is by bootstrapping the training set. Okay, so I'm going to sample with replacement from the training set to generate training sets that are artificial but have an equal number of bankrupt and non-bankrupt companies. Or in the other case, an equal number of private and non-private companies. Okay, so this is the rest of this is the usual cross-validation loop. And I just want to say I'm still going to test the model using the original test set. And so let me skip ahead to tell you how this thing performs. I've settled on random forests. The only other thing that actually works is boosting. Both of them are ensemble classifiers. The first 5 we tried, and we didn't get good results. Neural networks take a long time to train on this data set. The others, I believe, they don't deal well with missing data. So support vector machines and logistic regression in particular. As random forests, you have kind of a nice quote from the original paper by Bryman in 2001. It basically advertises a feature of random forests, which is that it has a built-in method for dealing with missing entries. And since my representation of the data incurs so many missing entries, that's kind of a key feature. Okay, so skip that. Just skip ahead to the results. So for the energy sector, my model is able to get an overall accuracy of 83.4%. So this is just looking at who invested in the company and the dates on which those investments occurred. For the private versus non-private problem, we get an overall accuracy of about 75%. And here's kind of the really interesting thing. If you look at the ROC curves, how many people here know what an ROC curve is, by the way? Okay, good. I'm in the right place. So I'm not going to explain what that is. I'll just show you the ROC curves. These things, I would say, are pretty good depending on which sector you look at, but what I especially like is the possibility of thresholding and sort of obtaining a classifier that doesn't attempt to classify all the time, which I think makes a lot of sense for this problem. I mean, if you look at the typical startup and ask someone to make a prediction of how well it's going to do after just 1 or 2 rounds, it's probably ridiculous to assume that you could successfully make a prediction of any kind or intelligently make a prediction of any kind for all companies. There are only going to be a few companies for which you're going to do this prediction well. So what you want to do is you want to focus on this part of the curve here and sort of threshold. Right? And the random forest gives you a really nice way of figuring out when to do this. Right? Because random forest is going to build a randomly generated collection of trees. Each tree casts a vote, and essentially the plurality of votes determines the class label. And so what you can do is you can look at how many trees voted for bankrupt. And if the percentage is really high, what these curves are telling you is you do a really good job of classifying. So let me give you the exact numbers. What you want to look at in terms of the ROC analysis is the area under the curve. So these numbers over here, this is very much related to Kendall's tau, which is just another measure of correlation in statistics. So this is telling you that we're getting ROCs of about 0.8. On average, what is it? It's about 0.83 averaged across all sectors. The accuracy averaged across all sectors is 75%. Okay, so again, 75% of the time, I can tell you whether the thing's going to go bankrupt or not. Okay, these are the results on predicting private versus non-private. The results are a lot more uniform across sectors here. There's a lot less variation. And so we get very similar results, though, in terms of the actual numbers. The average area under the curve is 0.83. The average accuracy is 75%. I will say this. Maybe the most important thing that I learned by doing this study is on this slide right here, which is the ranking of the attributes. Okay, so what you're seeing here is what the random forest is telling you the most important attributes are. So apparently the most important attribute is the date of round 1. So that's the date on which you got your first round of funding, which makes sense. I mean, if your first round of funding occurs during an extremely bad economic cycle, you may be doomed regardless of how good your product is and regardless of who's on your investor list. So apparently the classifier can tell a lot by that date. There's kind of a drop-off after that. There's two attributes which are almost equally important: the type of the investor in the first round and the identity of the investor. I was especially happy to see that the identity of the first investor in the first round is the third most important attribute, because that's the social network ranking. Okay, so that's this kind of thing that we kind of invented to model this data set. The other attributes here are all kind of, they're part of the raw data. Okay, so the main conclusion here is that if you use this representation of the data, bootstrap the training set, train with a random forest, you can indeed build a model that has decent out-of-sample predictive power. Not outstanding by any means. There's a lot of room for improvement here. Some of the more detailed conclusions: the type of the investor matters about the same as the social network ranking. You can see this from the ranking of the attributes. I already mentioned the thresholding and the sector stability for the private versus non-private problem. There's a number of ways in which we could improve this. Right now, my ranking of the investors is very simple. I'm just looking at the degree in the network. I could look at centrality measures, community structure, and I could also build a much more interesting social network. Right now, I'm saying if you invested at any point in time as another investor, I'm going to join your vertices. But I mean, that doesn't make sense. If you've invested at a point in time by which I've completely divested from the startup, then maybe we shouldn't be linked, right? Because we don't have any actual co-investment at that particular time. So that's what I call temporal edge weights. Haven't done that yet. Some other things that we could do would be to look at the dual graph, where the vertices are companies and you join two companies if they share a VC. And probably the most interesting thing is to try to better incorporate information about which VCs did not fund a company. I don't know how many people followed the Netflix prize, but one of the things that was written up after they won the Netflix prize was that the winning model actually modeled which movies were not rated by a user. So that kind of seemed like a very interesting thing to look into. If you're starting a company and a VC chooses not to fund you, that may be really interesting information. If there are any prospective grad students, I don't think I see anyone here who might fit that bill, but if there are, then please consider applying to the PhD program in Applied Math at UC Merced. We've got 7 tenure track faculty right now. We're expanding the program tremendously every year, and we are seeking to build in computational statistics. So thanks a lot. And
thank you
so
much, Bhat. So we have time for 2 quick questions so we can get into that schedule. Please.
So I was just wondering, you chose to approach this particular problem of how well the participation of different VCs can sort of predict later exits. Certainly, you know, a lot of VCs, by the time they get to the 3rd round, have a pretty good sense. I mean, in some sense, what the VCs would really love is before the 1st round, use the characteristics of the company to predict these kind of things. And I'm wondering if that or sort of any other sort of variation on this problem, are you thinking of not just as sort of an algorithmic extension, but actually as a topic-based extension to this work?
Yeah, I mean, that's a great question. I would say, I mean, as it stands, this could be used by mid to late stage investors. So I think the VCs you have in mind are kind of the people that jump in early after the seed stage of funding. But there are a lot of VCs and even private equity funds that would jump in much later. In terms of approaching the addition of content, though, I think one of the most interesting things is to look at balance sheet and income statement data sort of as soon as the company is founded, right? And so you can kind of detect whether or not there's any possibility of revenue coming in quickly. And so that would be a way to assess the probability of bankruptcy early on. kind of at the seed and maybe angel stage. Yeah. So we are looking into that. Yeah.
So I have one question for you. So have you heard something they call predictive index?
No.
So just all the companies that you look at when they look at their performance, that where they get to their. So for example, if you look at Microsoft, say, okay, here's in that categories here and there, but usually they look at only investment and the data that is profile of the company. But the other way to do these type of things that you're connecting everything to all the other companies. That,
right.
Okay, for example, if you look at Walmart, where is the Walmart connected to? Sony and everything that the products come to that one. So I think that would be the same thing, because you can add this type of the information to the companies. Because again, when the companies start building the technology, where are the companies that are connected or provide the raw material, or where is the target of these companies, which I have not seen in this one.
Right, absolutely. No, you could use a network approach for a lot of problems in financial modeling, and it really, I think, is a really exciting area for future research.
Great.
Yeah.
Thank you so much again
Thanks.
for having me here.